Did you know that our solar system is around 4.6 billion years old? That's nearly a third of the estimated age of the entire universe. Quite the mind-blowing fact, isn't it? But how do we know this? Well, scientists have used age dating techniques to study meteorites, which are among the oldest objects in the solar system. These ancient rocks are essentially time capsules, preserving precious information about the early stages of our cosmic neighborhood. The age of our solar system is not just a number, though. It's a testament to an incredible journey that began billions of years ago and continues to this day. It's a journey of creation, evolution, and discovery. Now let's take a moment to ponder what makes up this ancient system. At the heart, we have the sun, a massive ball of hot, glowing gas that supplies light and heat, making life possible on Earth. The sun accounts for a staggering 99.8% of the total mass of the solar system. Its mighty gravitational pull keeps everything else in orbit. Next up, we have the planets, 8 in total, each with its own unique characteristics. 4 rocky ones closer to the sun, Mercury, Venus, Earth and Mars, and 4 gas giants, Jupiter, Saturn, Uranus and Neptune, further away. But the solar system isn't just the sun and planets. It's also home to a multitude of smaller bodies. We have asteroids, rocky remnants left over from the formation of the solar system. There are also comets, icy bodies that originate from the outer regions of the solar system. And let's not forget the dwarf planets like Pluto, whose status as a planet has been the subject of much debate. It's a vast, complex system. But one question remains: how did it all begin? How did this cosmic dance of celestial bodies come into existence? So we know it's old and we know what's in it, but how did our solar system come into existence? The formation of our solar system is a wondrous event that took millions of years, and it all started with a giant molecular cloud in space. Now you might be wondering, what exactly is a molecular cloud? Picture a colossal chilly cloud formed primarily of molecular hydrogen, along with dust and other gases. This celestial entity drifting in the vast expanse of space was the cradle of our solar system. The story of our solar system's birth begins with the solar nebula theory. This theory suggests that at some point something triggered the molecular cloud, perhaps a supernova explosion or a shock wave from a nearby star. This trigger caused the cloud to collapse under its own gravity, and as it collapsed it began to spin, forming a spinning disk of gas and dust. The center of this spinning disk became denser and hotter, and it's here that our sun was born. This hot, condensed object at the center was the sun in its infancy, a protostar. Over time, as the protostar continued to gather mass from the surrounding disk, it heated up, eventually igniting nuclear fusion reactions and becoming the radiant star we see today. But what about the planets? Well, the spinning disk didn't just give birth to the sun. The leftover gas and dust in this disk began to stick together, forming tiny particles that collided and coalesced over millions of years. These particles gradually grew into planetesimals, the building blocks of planets. Over time, the planetesimals collided and merged, forming protoplanets and eventually the planets we know today. So our solar system, the sun, the planets and everything else, was born from the remnants of a collapsing molecular cloud. Imagine that. From a chaotic spinning disk of gas and dust emerged the beautifully ordered system of celestial bodies that we call our solar system. It's fascinating, isn't it? How the chaos of a collapsing cloud of dust and gas gave birth to the beautifully ordered system we call home. Now here's a conundrum. The outer planets, known as gas giants, are composed mainly of hydrogen and helium. But these elements were scarce in the inner part of the solar nebula where the planets formed. So how did they get there? Let's delve into the theory of planetary migration. It's a notion that describes how planets might shift their positions after formation, like pieces on a cosmic chessboard. The key players in this game? Gravitational interactions. Imagine the early solar system as a swirling disk of gas and dust. Planets start to form, gathering mass and exerting gravitational force. As they grow, their gravitational pull disrupts the surrounding gas, creating waves. These waves then push the planets, causing them to move. The gas giants, with their massive sizes, would have created substantial waves, leading to significant migration. It's like dropping a massive boulder in a pond. The resulting ripples can cause smaller objects to move. Now, consider the direction of this movement. The inner solar system, where the gas giants initially formed, was dense and heavy, so the gravitational waves here were stronger, pushing the gas giants outward into the less dense outer solar system. This planetary migration could explain how the gas giants ended up where they are now, composed mainly of hydrogen and helium, elements that were scarce where they initially formed. The solar system, as it turns out, is not as static as you might think. The solar system we see today has evolved over billions of years and will continue to do so. Our solar system is not a static entity, but a dynamic, ever-changing cosmic arena. Over billions of years, it has undergone dramatic transformations and will continue to do so long after we're gone. From the birth of the sun and the formation of the planets, to the creation and destruction of asteroids and comets, the solar system's evolution paints a picture of cosmic resilience and transformation. Now let's talk about the future. Scientists predict that in about 5 billion years, our sun will exhaust its nuclear fuel. It will swell into a red giant, engulfing the inner planets, including our own Earth. But don't worry, we've got a good few billion years to figure that out. After this fiery demise, the sun will shed its outer layers, leaving behind a small, hot core known as a white dwarf. This remnant will cool and fade over billions of years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will survive, but they'll be left to orbit a ghostly, dim sun. The solar system's evolution doesn't stop there. Over trillions of years, it's likely that gravitational interactions will scatter the planets, potentially ejecting them from the solar system entirely. The story of our solar system is a testament to the ever-changing nature of the universe. So, buckle up for this cosmic journey, because the history of our solar system is still being written.